Well, good evening, ladies and gentlemen. I'm Jack Daly, the John and Adrian Mars Director of the Smithsonian's National Air and Space Museum, and it's my great pleasure to welcome you to the National Air and Space Society's Vice Admiral Don D. Engen Flight Jacket Night. Time flies just like everything else does in this here place, and in more than 20 years since we founded the National Air and Space Society together, our members have contributed more than $20 million to support our mission to commemorate the history of flight and inspire its future. And that support has never been more important. Over the next several years, we will completely rebuild this museum from the outside in. In addition to revitalizing the building's exterior and mechanical systems, all 21 galleries will be redesigned with latest technology to meet the challenges of the next 4 decades. The brand new Boeing Milestones of Flight Hall, which you passed through on the way in tonight, is a taste of the innovative new visitor experience we're bringing to all of our new exhibitions. As longtime patrons, you know how critical private support is to this museum. Our federal funding provides just a portion of our budget. We need the help of sponsors like you to deliver the programs, events, and exhibits that have made us America's most popular museum. We will remain in operation throughout the multi-year renovation, and NAS members are our best ambassadors. So we ask you to tell your friends, family, and strangers on the street that we are open despite the dust in construction. Tonight we celebrate the memory of Vice Admiral Don Engen, our former director. As a naval aviator, Don distinguished himself in 3 wars. As a test pilot, he helped develop safety measures that saved hundreds of his fellow flyers, and he carried that focus on life-saving technology through his tenure as chief of the FAA. Don led this museum through a time of change and challenge, and his family continues to build on that legacy today. As we begin a new era of transformation, I want to thank the Engens for everything they've done and continue to do for the museum. On April 1st, 1916, Elmer Stone, Lieutenant Elmer Stone, reported to Naval Air Station Pensacola to celebrate the for flight training, making the birth of Coast Guard aviation. To celebrate the centennial of that auspicious occasion, we welcomed the very first Coast Guard aircraft into the National Collection this spring, a Sikorsky H-52A, Sea Guard, now on display at the Stephen F. Udvar-Hazy Center. But the Coast Guard's role in the history of aviation goes back even further than that, to the day in 1903 when surfmen from Kill Devil Hill Lifeboat Station hauled the fragile Wright Flyer up the beach for that first flight that transformed the world. Aviation is America's story, and from the sands of Kitty Hawk to spaceflight, the men and women of the United States Coast Guard have been there every step of the way. And one of their highest flyers is here with us tonight to discuss his remarkable journey. Captain Daniel Burbank earned his commission from the United States Coast Guard Academy in 1985. After attending naval flight training in Pensacola, he served at air stations from Elizabeth City to Alaska, eventually logging more than 4,000 flight hours, including 300 search and rescue missions. He was selected by NASA as an astronaut candidate in 1996, and in 2000 made his first space flight as a mission specialist aboard the Space Shuttle Atlantis. That mission paved the way for the first crew aboard the International Space Station, which was not inhabited at that time, and which has now become our permanent outpost in the sky ever since. Another flight aboard Atlantis in 2006 saw Captain Burbank's first spacewalk, during which he installed a massive truss on the ISS structure and deployed 2 sets of solar arrays, bringing the station closer to full operational status. Next came a stint as professor of engineering at his alma mater. Finally, in 2011, after having flown missions to activate and complete history's most complex orbiting laboratory, Captain Burbank returned to the International Space Station, this time as commander of Expedition 30. From life-saving missions as a Coast Guard aviator to homesteading the new ocean of space, our guest tonight has pushed the envelope of achievement his entire career. And we're grateful that he's here to share it with us tonight, and it's now my great pleasure to introduce Captain Daniel Burbank.
Thank you very much, General Daly, and thank you Friends of the Smithsonian, thank you for the staff and the general as well for the invitation to come here and spend a little bit of time with you tonight. That was a great introduction. I'm not sure I'm worthy of number one, even being in front of you here to talk to you. We've got so much experience, so much knowledge about the space program, about aviation in general. I'll try to give you the pieces that I know, and I'll try to give you the personal side of it a little bit. Some of the stories about flying in the Coast Guard, a little bit about what it's like what it feels like to launch on a shuttle. Maybe give you a sense for what it's like to live on board the space station, and try to leave a little bit of time at the end to answer some of your questions. So, as the general mentioned, this is a very big year for us. Elmer Stone started his aviation training 100 years ago this past spring, but we also had this letter you can see on the right-hand side of the screen that also was kind of the kernel of maybe aviation engineering in the beginning of aviation operations. So we had only been flying planes, human beings, for just a handful of years at that point, and there was a Coast Guard cutter captain, a CO, who had some conversations with some of the staff and engineers of one Glenn Curtis of aviation fame that we all know well. And they basically sat around the wardroom on the Onondaga, this Coast Guard cutter, and kind of brainstormed on things you might do, how you might apply helicopters, or actually airplanes at that point, to potentially create a means to do search and rescue more efficiently, to have to basically put eyes higher in the sky, and to potentially reach out and reach those in distress more easily and more efficiently than you could with ships. So it's kind of an interesting document if you read the words there, and it's very prescient. And it's the very bottom, he talks about how they'd probably be saving hundreds of lives. And if you think about it, just the Coast Guard alone, in the couple of weeks that surrounded the Hurricane Katrina disaster in New Orleans, the Coast Guard alone saved on the order of 22,000 lives. So, and that was with the aircraft, but also with surface assets as well. And in a typical year, there are many thousands, around the world, not just by our Coast Guard, but many thousands of people that benefit. They find themselves in harm's way, and they benefit by aviation assets applied in that way. 3 years after Elmer Stone finished his flight training, he made the first successful crossing of the Atlantic in the NC-4, NC, the Nancys, I guess they were called, but NC for Navy Curtis, and it's a flying boat. And in that configuration, there were three of these aircraft that tried to make their way from New England over to Europe, and just this one made it. It wasn't single-handed, of course, and it wasn't in a single leg, as Charles Lindbergh did, 8 or 9 years afterwards, but it was the first. In this case, Elmer was on a member of a crew of 6. He was the pilot. So over the years, we had lots of experience, and this is just a tiny sliver of the different kinds of fixed-wing aircraft that the Coast Guard had used, including some long-range seaplanes like the PBYs. The airplanes you see on the left-hand side are HU-16 Albatrosses, and it's a variant of a predecessor aircraft too. We had many, many of those. Those were still in service when I joined the Coast Guard Academy. Unfortunately, they weren't still an option to fly when I was getting out of flight school. That might have been the only thing to persuade me to fly something besides helicopters, which, by the way, for the Coast Guard, that's like fighters. That's where the action is, and that's what everybody strives. Well, I say everybody. That's a little biased, admittedly, but I think if you as a pilot, if you as an officer in the service want to actually participate hands-on in saving somebody's life, the way to do that obviously would be in a helicopter. Those kind of airplanes, the HU-16s, of course, can land in the water, amphibious, just like the PBYs before it. We've got lots of long-range search and rescue airplanes like the Workhorse, the Hercs, the HC-130s. And there's even UAVs that are being discussed now as well. So there'll be new assets that I think the Coast Guard will bring to bear, just as other services had. Vertical flight's key for search and rescue anyways, I think. On the upper left there is the HNS-1, which is piloted in this picture by a guy by the name of Frank Erickson, almost of the same level of fame within Coast Guard aviation circles as Elmer Stone. And I think he was the first person to actually complete a hoist, actually designed a hoist to be used in a helicopter, and actually hoisted a person with it and did some testing with it. And that airplane served for quite a few years, even on board ships, and paved the way for some of the follow-on workhorses. The one on the upper right-hand side there, the H-52 H-2, single-engine helicopter, amphibious, powered by the same engine, but that the H-3, the picture directly below it, would have. But if you can imagine being out in dark and stormy nights, maybe up in the Aleutian chain, and powered by a single engine, and anybody that's a helicopter pilot, if you're flying a single engine helicopter, you're always looking from field to field. If something bad happens, what you're going to do at that point. There's not a whole lot of fields out there in the open ocean, and lots of folks have flown those. The very first time I flew in a Coast Guard helicopter was in that. And as the General mentioned, we've got a great example of one at Udvar Hazy out here that's just recently restored, and we're real thankful to have that out there. I flew the H-3s for quite a while, and then I flew the H-65s later. The H-65s briefly, and the H-60s, which are on the lower left there. So as I was growing up, there were probably two major formative events for me that kind of dictated where my life, the path my life took. If you asked most astronauts, I'd say, when they knew they wanted to be an astronaut, I think most of them would tell you when they were kids, and maybe they saw something like this. This was about a week before my 8th birthday, July 20th of 1969, and this was a momentous thing, probably on a scale that many of us here in the audience recognize, but it impacted the entire world. This was not even America's achievement; it was an achievement for all of humankind, and everybody stood up and took notice, and it was something we could all be very, very proud of. As a young kid, I was there with my sister, who's in the right of the picture, with our binoculars. We begged our parents so we could stay up late enough to see the spacewalk itself. They landed, I think, early evening at East Coast time on that day, and the spacewalk wasn't until about 11 o'clock at night. And we were pretty sure we could see them with those binoculars. They're pretty good. But and by the way, our friend in the middle there, Neil Johnson, who I was infinitely jealous of for that first name of his. But anyways, for me, I was this made me a fan of space and passionate about the space program, and made me interested in astronomy. I learned how to build telescopes, grinding mirrors, and doing all that. But I never wanted to be an astronaut, unlike a lot of my peers, and that is because I think this, even at the tender age of almost 8 years old, seems so far beyond the realm of feasibility. This was a different class of people. This was a different level of talent and smarts and all the rest. But I certainly was a fan from that point on. So the other major formative event happened a year later, and it's as silly as it sounds. This is a Walt Disney movie called The Boatniks. I don't know if anybody remembers this, but it made a big impression on me. It's a goofy movie about this fella that graduates as an ensign from the Coast Guard Academy, and he goes to his first unit, and it's a patrol boat, and he has a whole series of misadventures, and there's like jewelry thieves and different criminals he has to interdict it, and it's just in classic Walt Disney fame, ridiculous to the core. But at that point, from that point on, as far as I can remember, the next 10 years, what I wanted to do was search and rescue. This idea that you'd have a Coast Guard, that you'd have people that would potentially go charging out on little small boats in stormy weather and rescuing people, just captured my imagination. So long as I can remember, that's what I wanted to do. So I applied to the Coast Guard Academy, and I didn't get in. So I went to another school for a couple of years and majored in physics, and then decided to reapply, and I got in on the second try, and started in at the academy in 1981. And it was one night, I imagine we still do this. We certainly did it back in the day, but every night you do a lot of push-ups in those early mornings. Swab summer, we called it, plebe summer, or what have you. But it was a lot like boot camp. And you'd finish all those push-ups with the rest of your squad mates or company mates, and then everybody would be sitting on their bunk and with a flashlight on their shoulder, maybe reading this little book that we called The Running Light. And it's a book full of all the trivia you had to know if an upperclassman got in your face and quizzed you about something or other. And as I'm reading through this, trying to memorize all these things, write them to my hard drive, I realized to my horror, there's a section in there that talks about Coast Guard small boats, motor surf boats. Motor surf boats, if you've seen the Finest Hours, these are the boats that were stationed all around the coastal areas in the U.S., and folks would literally charge out in the stormy weather in them. That's what I wanted to do. Well, the equivalent of those, these kind of small boats, then I realized as I was reading this that the only people in the Coast Guard that could not be on those boats are officers. because you're too senior. Our enlisted men and women are the ones that do those missions. So the first message here is thoroughly research your career goals. So I'm 10 years into this dream, and when I suddenly realized this, and I didn't know a whole lot about the Coast Guard beyond that. This is like day 2 or day 3 or something. So a couple pages later, I realized, wow, the Coast Guard's got big ships. That's interesting. And then they had pictures of airplanes that they had, and I was completely unaware of aviation and that aspect of the Coast Guard operation. And then at the very end of those couple of pages, it had these helicopters, the H-52, the one that we have out here at the Dulles place at Hazy. And I realized that this would be something that, as an officer, you could do, and you would be doing the same kinds of things that the Coast Guard men and women that charge out in those surf boats do. And how cool would that be? And up until then, it had never occurred to me to even consider flying. And I think from that point on, I never thought of anything else. So after a tour on a ship, we all did that back then, a great tour where I learned a lot about the things that ships do and how to work with ships on things like search and rescue cases. I got to go to Navy Pensacola and earn my wings of gold, as many of us do. About the time I got there, this happened. There's this Coast Guard fella flying H-3 helicopters, the twin-engine ones, and he got selected by NASA to go and be the first astronaut representative of the Coast Guard. And up until then, you know, my path for what I thought was realistic and what I thought I just dreamed about, and this was this ethereal, amazing thing that took place by otherworldly beings called astronauts and the engineers that built rockets and things like that. Suddenly those kind of intersected, and there was this possibility. So Bruce had a great career with NASA, and after 2 space shuttle missions, including one in which, and as is depicted here, he and his crew captured by hand an Intelsat 6 spacecraft. They had a mechanism designed to interface with the back end of the spacecraft. The spacecraft was stranded in an orbit that was useless. Its kicker motor didn't work, so they had to basically bring it into the payload bay and put a new motor to get it up into a geosynchronous orbit where it would be useful. And the mechanism to allow them to capture this didn't engage with the satellite. So the only way they could do it was to send 3 people out in 3 spacesuits at the same time, being one of which was on the end of the space shuttle robotic arm that Bruce was operating. And they caught this 3-ton satellite that was spinning in the payload bay. I don't know if you recall any of that, but there was a lot of debate, a lot of controversy about this, and whether this was even possible to fit 3 people. If you've ever seen the size of a space shuttle airlock, it's almost inconceivable you can get 2 people in there, let alone 3. The way the communication system is set up for the EMUs, the spacesuits, only 2 people could talk to each other. The other one would have to be on a different radio. And figuring out how you would coordinate the radio swaps and the hand signals to be able to safely do this was pretty amazing. But the beauty of this was classic Coast Guard operations. This was the way, the Coast Guard's a very flat organization. The kinds of conditions the Coast Guard operates in, the kinds of missions that we do, requires there to be a level of autonomy bestowed upon the helicopter crews or the ship crews or the small boat crews that's a little bit unusual in most other military outfits anyways. And it's the physical dislocation, it's communication challenges, it's the hazardous environment, a lot of other things. But the model for how a rescue coordination center on the beach would oversee the conduct of a search and rescue operation that had many different assets out in the field in bad conditions with spotty communications was really similar to the way mission control would work with shuttle crews, for example. So there's, obviously the mission control and the flight director runs those missions, but when you're out there in the spacesuit on the day of, the crew has got to be able to make real-time decisions, and they're trained to do that, and they practice that. So I think the Coast Guard's actually a pretty good proven ground for those kinds of things. And there's another aspect of it I'll talk about in just a bit. So my first air station was Elizabeth City. I spent 5 years there, and during those 5 years, I got to be an H-3 first pilot, aircraft commander, and eventually an instructor pilot. And then I transitioned to the H-60. We had just received this great variant of the Army Black Hawk and Navy Seahawk that we call the Jayhawk, which has got 3 big external tanks that can fly for 6 hours. Not that anybody wants to be in a helicopter for 6 hours, but it can, and it can go a long ways offshore, and it can spend a lot of time out there, and it can come back. The curious thing between the differences between an H3 and an H60, they're roughly the same gross weight. The H60's got it's a little bit faster. They have about the same legs, about the same distance they can travel. The volume, though, in an H3 is massive. It's huge relative to the volume in an H60. But the H60's lift capability, the excess power that you have with the engines that are there, is pretty impressive. So the H60 is designed to pick up 8 survivors. I think that's kind of the spec. So you have a pilot, a co-pilot, a flight mechanic, a rescue swimmer, and you got provisions for 6 or 8 people comfortably. But people are not dense enough in general that you can't fill an H60 from the floor to the ceiling and still not have enough power to do the mission. So I've had 13 survivors in the back. Many other crews have had a lot more than that in there too. And an H3, I think it'd have to be something like those little packing peanuts, and then you could fill that all the way up to the top. No disrespect to the H3, it's a wonderful, wonderful airplane and has served for many, many years in the Coast Guard. The ability to land in the water is also a tremendous thing. And we would practice these sporty high sea state rescues where you'd actually touch down at the top of a wave crest, in an H3 and try to pick somebody up. But there's still not enough to be said about how wonderful it is to have lots and lots of excess power like an H60. So while I was there at Elizabeth City, we had this thing that happened. Let me set the stage first. We had lots of World War II era assets, some of which were like this, the Coast Guard cutter Tamaroa, which was an ocean-going tug that dated back again to World War II, about 200, maybe 205 feet or so, I think, long. It kind of had this joke about it. It was called the Coast Guard's only submarine because it had sunk at the pier, so to speak. That's actually disrespectful. He didn't put it that way. What had happened is it was in for overhaul. It was in the dry dock. It had a big hole cut in the side of the hull, and they were putting in new engines and new generators. And something happened with the dry dock. Valves got misconfigured. Something happened, and the dry dock basically went down, and it took the Tamaroa with it. And what should have been a reasonable year or so refurb ended up being a heck of a lot longer and more costly than that. But the Tamaroa, quite proudly continued on and had many, many decades of service after that. One of those, probably it's the highlight for it, was this storm that didn't have a name back then. We call it the Halloween storm maybe, but back in October of 1991, and Sebastian Junger, I think, wrote a pretty good book about this, and there's a movie about it. But this was a huge storm, obviously you all know, and it covered the entire Northeast, and there was many, many vessels impacted by it, lots of assets, lots of search and rescue assets supported it, ships, helicopters, not just Coast Guard, but also a rescue unit out of Suffolk, Long Island. Anyways, the Tamaroa, and so I got a chance to participate a little bit in that mission at the tail end of one of those. It was after this MH60 out of Suffolk, Long Island, had to ditch. They basically got below their bingo fuel, ran out of fuel, and in sea states of upwards 30 to 40 feet, and winds probably gusts well over 80 knots, ended up in the water. And one fatality, and I think 4 survivors. I was down in Elizabeth City, North Carolina. This storm was big enough that we had a case that we were already flying that was down off of Cape Fear, and then got diverted to another one up around Navy Norfolk. And then we heard about this thing that had just happened, and the Tamaroa was up nearby. They were trying to help out, I think, a sailing vessel that was in distress off New Jersey, south of Long Island. Anyway, so we got on scene. It was really, really dark. I put a couple of pictures here. This is like a day after the height of the storm. And to give you a sense, again, this is a pretty good-sized cutter. It's not a destroyer or anything, but it's 200 feet. And there's times when the screws are sticking up out of the water in the backside, and the bow is completely underwater, back a third of the length of the ship. And the other times they're popping like a cork out of the top of one of these waves as they came. And this is when the seas had calmed down. We didn't have cameras. We got there, and it was dark. It was blowing like crazy, and it was the winds were howling. It was probably good 40 foot, I think, rollers periodically that we would see. And our job basically was to hold the flashlight for the heroes on board the Tamaroa who rescued those folks from the H60. And it was an amazing thing to see. So if you can imagine, and the H60 is a great helicopter to be in those kind of conditions, stable as could be, and you're high and dry, and again, plenty of power. You didn't worry so much about that. And we could stay in a hover, and it wasn't like an a hover. We were like in forward flight at 80 knots, but we were over the top of where the Tamaroa was, and these folks were in the water nearby. And the Tamaroa had a cargo net draped over the port side, and they had cables strung, I think, from the bow to the stern, and all their crew that were up on the deck, had these lifelines on, and they were snapped into that cable. And and we had night vision goggles, so you could see all of this stuff and watch it as it was going and kind of keep track of where the survivors were. And use our searchlights to kind of help them illuminate. But periodically, you'd see one of these waves come in. It would crash over the bow, and the Tamaroa would glow this eerie green as the deck lights were kind of shining up through the water. And you're like kind of holding your breath, counting those seconds, because there's people down there right now you're looking at that are underwater trying to do this amazing job that they're doing. So we decided that experience as the Coast Guard's only submarine stood them in good stead. They did a great job, and they spent a lot of that night underwater, and there's a bunch of folks that were able to come home to their families as a result of it. So then after Elizabeth City, I went to Cape Cod, and while I was at Elizabeth City also, I entered a Coast Guard aeronautical engineering track. So it's a separate career path within the aviation ranks, where you're going to be doing a lot of test activity, maintenance test activity on airplanes. The troops that work on our airplanes, all of which, by the way, are air crew that actually are operationally qualified in our airplanes and helicopters. So they would be the ones you'd kind of oversee the maintenance effort to keep those helicopters flying. So I was the assistant engineer when I got to Cape Cod, and I was up there for 3 years, and then I went up to Sitka, Alaska after that. Cape Cod was good because you could learn how to fly in ice and fog and snow. And the snow part was probably useful for Sitka, but there was another thing that you had to learn how to do when you got to a place like Sitka or Kodiak, Alaska. So the Coast Guard does a business up in that part of the country that's a little bit different than where we do what we do elsewhere. And that is, we because it's not really feasible to have a company be able to provide something like an emergency medical service capability. And you've got lots and lots of remote villages scattered all about. The only outfit that can really do that and do it safely is a government outfit like the Coast Guard. So the Coast Guard would do a lot more inland search and rescue in a place like Alaska than they would elsewhere in the lower 48. And the interesting thing about it is you don't fly like you do normally in the lower 48, where you're using VFR or IFR charts. You're not shooting approaches. In fact, you're going to avoid getting in the clouds if at all possible, because it probably means you're icing up. But in Alaska, you're going to fly mostly with the topographical charts that hikers use. So you're going to basically be flying a lot of the time on goggles and working your way, nosing the aircraft up through some box canyon, over a saddle, and down some little path that's poorly marked in this little chart, and with some scribblings and so forth that you and your folks had put on it. And that's how you fly. That's what you do up there. So you can go there and be the most experienced aircraft commander or instructor pilot in the world, and you're nothing the day you show up in a place like Sitka or Kodiak until you learn those skills to be able to fly like that up there. But it was while I was, and I'll back up a little bit. So I had applied, after Bruce got selected, I applied very optimistically before I was even an aircraft commander while I was at Elizabeth City. And I got an interview, and I came to NASA and interviewed and got turned down. But gosh, it was so great being down there for that week. And then while I was at Cape Cod, I applied one more time, got another interview too, which was really great, and got turned down. And then applied one more time, and then while I was at Sitka about a year and a half in, I got selected to join NASA. My mindset going through those interviews, and by the way, I would never get in, I don't think, in the current day and age, because we have so many people that know about the space program, so many people that are talented and prepared and ready to do it and excited about it. This is a really neat time. We had over 18,000 applicants for a class that we're going to select for next summer that'll show up, and we may hire 8 people, we may hire 14, somewhere in that range probably. So it's pretty tough. My mindset, though, on all those interviews was I had no expectation of ever getting picked up, and I was delighted they'd invite me down to interview, and I would accept the medical tests, painful and difficult as some of those might have been, and be glad just to hang out with these incredible people, not the astronauts alone, but also the engineers and flight directors and flight controllers. So it was pretty neat. So I was going to look at that as my career collateral duty. I would just do that on the side forever, and it was pretty shocking when I finally did get picked up to go. Okay, so I'm going to pick it up a little bit because I'd like to have some time at the end to answer some questions. But the class that's going to show up next summer, this is kind of what we're going to do to them, and this is what we did to the 35 folks that joined with me in 1996. You're going to go through astronaut boot camp, and it's about 2 years long. And back when I went through, you're going to learn about space shuttle and space station. We don't do as much printed material as we did back then, but that stack that's under my left arm right there is the equivalent of the flight manual for the space shuttle. So it's a diabolically complicated, very non-intuitive, but extremely robust from a redundancy standpoint design. But it's got something like 829 switches, I think, on the flight deck, depending on which vehicle you're talking about, 460-something circuit breakers. And those things are laid out and organized in a way that kind of defies what you would think of as common sense. So it takes a lot of time in the books, and the books were pretty formidable. All the books in the bookcase there, most of those are space station and some of the shuttle operations ones like robotic arms and stuff. A lot of time in simulators. So it's just crash course, fire hosing. For people who are military aviators, a lot of that kind of had the same sort of feel and as flight training at Pensacola, or learning a new type rating in a different aircraft. You get what we call enrichment training, which is basically learning all the different things, the different science disciplines that are relevant to flying in space. So it could be geology. We do it on a macro scale now from space. We're going to do it up close and personal, we expect, on Mars and on asteroids and perhaps on the moon as well. We learn about solar physics. We learn about astronomy, oceanography, meteorology, orbital mechanics, on and on, all the different kinds of things that are relevant that you need to know. Some people in the class will be experts on a couple of those different areas. It doesn't matter. We all go through it. And NASA will bring in experts from all around the world, the best folks on whether if it's something about field geology, for example. We were trained by the same folks that trained the astronauts that did the Apollo missions. Then we do a lot of flying in different kinds of aircraft. So the space shuttle, the cockpit is the one on the left there. You can see some of those switches, and you guys know a lot about all that. The space shuttle has this incredible challenge of being able to fly at 17,500 miles an hour, Mach 25, and they've rarefied upper extremes of the atmosphere, being able to fly there, and also being able to fly at a speed that a human being could land the thing when you get down low, when the atmosphere is dense and you're over the runway. So it's a compromise, but it's a beautiful, elegant, incredibly sophisticated compromise. To be able to, so just to do a quick apples and apples conversion. A typical airliner, most airplanes are going to come in at about a 3-degree glide path at maybe 150 knots or something like that, give or take. If it's a jet airplane, it may go quite a bit faster. But the shuttle is going to come in at 300 knots at 20 degrees. So it's going to come in twice as fast, and it's going to be at 8 times the glide path. So the only way, so if you're going to train in an airplane, a flying simulator, to be able to fly that vehicle, the only way to do that is to make it fly like a shuttle. And to do that, we took a Gulfstream, and you deploy the thrust reversers in flight, and you basically make the engines run at nearly full throttle, trying to pull the airplane back uphill. And then it'll fly as badly, quote unquote, or as aggressively as a shuttle will. And so before any pilot or commander is ever going to land a shuttle, they would have done 500, probably 1,000 dives in the STA, the shuttle training aircraft. So the Gulfstream is modified in other ways too, but those are probably the principal ones. The cockpit on the left side is just like the shuttle cockpit above it, generally. The cockpit on the right side is just like an airplane, just like a Gulfstream, so it's got a yoke and it flies. You flip a couple switches and it'll fly like the Gulfstream. And you flip a couple other switches and it'll fly like a shuttle. And you can make it fly like a shuttle in a certain mode. You can make it fly like a shuttle if the shuttle had engines that could push it through the air in level flight. And you can do some interesting things. Not that it was relevant for the flying, but anyways, a beautiful airplane and a pretty challenging engineering exercise to get it to do that. If we want to replicate microgravity in an airplane, the only way we can do that is by flying parabolas in an airplane like this, the KC-135. We've done it with C9s. We've got other airplanes that'll do it as well. And you can get about 30 seconds of zero gravity, quote unquote, microgravity over the top of a parabola, followed by 2 Gs of a pullout. And you do 40 of these, 40 or 50 of these. So this airplane, aptly called the vomit comet because of the provocative nature from a vestibular sense that those parabolas would be, it would give us these tiny slivers of what it would be like to be in space. It's really hard to be anything but a klutz if all you've done is just little slivers of 30 seconds. So Shuttle crews were it was very difficult to do that adaptation for the first couple of days, but it was still a lot of fun to do this. The first couple of flights you do in there, you just play. You can release a cloud of M&Ms, go flying through it. They'll let you squirt a big ball of juice and do any kind of crazy thing you can imagine. But it was a real tool. It is a real tool. We can test hardware. We can do work on the EMU, for example, test out a new cooling system pump. We can test out, like I am in the upper right there, in an EMU, testing out tools and techniques to repair shuttles should we incur damage like Columbia did. But but not everybody liked that. Another simulator that we have really is the Neutral Buoyancy Lab. If you're in a spacesuit and you want to practice a spacewalk, you in the spacesuit on dry land weigh about 500 pounds, maybe 600 pounds with ancillary tools. You can actually stand for a couple seconds like that, or even a minute or so, but if you fall, you're going to need a team of people to stand you back up, and you could not practice like that. But you displace about the same amount of water. That volume of you in that suit displaces the same weight in water as the suit, and you weigh. So you can do this neutral buoyancy thing and practice in a pool like the one that we have here, which was a new one designed specifically for the space station. 6 million gallons, 200 feet long, 100 feet wide, and 40 feet deep of just crystal clear blue water, and the entire space station, albeit with some appendages folded in different ways, can fit in there, as can space shuttles. It's a lot of work because you in the suit may be neutrally buoyant, but you inside the suit are not. So you might have to be upside down for a couple of hours during the course of a 6-hour EVA, and all the blood's rushing to your head, and all your weight is being borne by the neck ring that supports the helmet. It's like you're doing a headstand in a trash can, and so it's digging into your shoulder, and it's a very challenging thing. It's like running probably a half a marathon, but it is so much fun. The other things we do, we got virtual reality training. We had some great motion-based simulators for the shuttle. We're developing the simulators right now for Orion, for SpaceX, and for Boeing. 3 new spacecraft we're getting ready to fly soon. We had, and we would do lots of suited training, at the end of which 2 years is done, and now you are ready to be assigned. And then you'll wait, and you'll support missions. You'll be a Capcom. You'll be maybe working over in Russia, helping them with some test activities and some of their modules, and doing a whole host of other things that we do until you get assigned to your first mission. So STS-106 was my first, and the general had mentioned it earlier. Our job was basically to haul up all the stuff that could not be in the service module when it launched because its rocket wasn't strong enough to lift the entire thing fully outfitted. So there was several of us that actually were in Russia for a lot of the testing on a lot of that equipment, and then many of the heavy things were brought out, and 6,000 pounds of it was stored in the back of the shuttle payload bay. We brought that back up, docked with Space Station. The 5 U.S. crew members and our 2 Russian colleagues spent a very busy 11-day mission, installed all that stuff again, treadmill, oxygen generator, big 200-pound batteries, lots of other electrical equipment, and then made that space station habitable for the first crew that would show up in a couple of weeks. As an aside, the very first tool that I ever wielded on the space station was a mallet, actually a big sledgehammer with a head about this big and a cold chisel to cut a piece of secondary structure out of the floor of the functional cargo block in one of the Russian modules, so that we could put that little electric box here you can see in the lower right, so that Boris Morikov and I could install that. I didn't even know you would have something like a sledgehammer in a space station. But very delicate, delicately. So a great mission, very busy, and then I got back to doing other things, and fairly soon, about a year or so later, got assigned to my second mission, which was STS-115. This was to be a 1.5-year train and flow, and as we were within our last 5 or 6 months, we lost the shuttle Columbia, and that changed everything for everybody. So our training flow became on the order of 4.5 years, and there was an awful lot of work that all the operational and engineering community had to do. We had to understand what had happened to that vehicle. We had to understand how to prevent it again. We knew we still needed the shuttle because there's nothing like that can bring up 35, 40,000 pound payloads, stage a spacewalk, do all the robotics activities, and build what's now a nearly 1 million pound space station. Absent the shuttle, we didn't have the means to be able to remotely, autonomously launch the various pieces and parts up there. So we had to get the shuttle. We had to get it flying safely enough so that we could, in good conscience, put crews on there and get those last, many missions out. So it flew quite a bit more missions, but all those missions had a lot of activities where we developed sophisticated scanning techniques to use the robotic arm with all kinds of extra tools to make sure that the wing leading edge was intact, to make sure we did all kinds of extra photo documentation. We flipped the shuttle on its back right after we separated from the external tank so we could quickly get high-res imagery to make sure no foam was missing from the tank that might have, on the way uphill, struck the shuttle. So, and then there was all the capability of being able to go out and do an EVA in case something bad had happened, to be able to fix it. And we would plan for things like shelter in place. So say the orbiter was just flat out unserviceable, no way we could fix it, then we would have to stay on board station, and we'd have to have a means to get some lifeboat, capability to recover a crew. So a lot of those missions, those from STS-115 to STS-135, had a tremendous amount of work that went into them to make them safe enough to be able to operate that. But it was critical for the space station. So it was about a year before I was getting ready to fly. Now Columbia's behind us. We're getting close, and we're about ready to go, and Katrina hits New Orleans. Massive storm. I think Cat 4 when it probably made landfall, and just basically a bullseye right on top of New Orleans. The Coast Guard, again, being a really flat organization, what they usually do when hurricanes come in, and even this last one, I think a couple of weeks ago, Hurricane Matthew, we'll move all of the assets, all of the airplanes and helicopters away from harm's way, as the storm comes in. It's always a little strange when you climb in those helicopters and evacuate, and your family's back there, in the house saying, hey, and all the crews leave. But we'll typically evacuate all the helicopters and airplanes and then kind of position them to sweep in behind the storm after it comes through. So, and I participated in one of these way back, Hurricane Hugo, when it hit Charleston, South Carolina, many years ago when I was in Elizabeth City. But it's a tried and true technique. This was on a massive scale like nothing the Coast Guard had ever done before, though. So essentially within, I think, 12 hours of the storm making landfall, we had 1/3 of all the Coast Guard aviation assets that were physically on the Gulf responding there. And we basically, very quickly, used up all the crew time, all the available per rules time that anybody could fly, and we were starting to fly. Even if we couldn't get helicopters from Alaska down there, we were sending crews, flight mechanics and rescue swimmers and pilots and co-pilots down, and they would just jump into whatever helicopter was available and just continue all the rescue ops. And in the course of probably a couple of weeks, I think something in the order of 22,000 people's lives were saved or assisted in the course of that. And so again, this is that, and the beauty of how that worked is, and this is where I think it's kind of the standardization of how you operate, the ability to, you could say, we've got a critical operation, extremely hazardous conditions, and we need to be able to send out an asset, and we're going to put a pilot with a co-pilot he's never met, and a flight mechanic and a rescue swimmer. We're going to throw them in this helicopter that they know how to fly, that they're qualified, but they've never ever worked together, and they're just going to go out on some dark stormy night, and they're going to do some pretty hazardous ops. They're going to maybe do some vertical rescue. We're going to deploy the rescue swimmer to some steeply slanted roof where people are trapped inside and the water's rising and they're in the attic, and this rescue swimmer is going to figure out a way to cut through the roof with an axe or a chainsaw or something else. And at the same time that's going on, about 2 doors down, there's going to be another helicopter, and there's going to be a bunch of Coast Guard motor surfboat type assets, surface assets running around as well, with no good comm structure. All the power's down, so we're basically building all that stuff as we go. And just by the way, by having a flat organization and people that are really, really motivated to do what they do, but that train meticulously so that the way they talk, the things they do, how they operate, you almost don't even have to say anything because everybody knows what everybody else is thinking, and that's a thing of beauty. And to be able to take that and apply that to a space mission, I think is kind of the holy grail for us right now. There's a lot of discussion. We debate now about how to make crews as efficient as they possibly can. How do we meet all the challenges of training a crew to fly 1 million pounds of hardware on board space station when they're only going to overlap with some of their crewmates for a few weeks during a year-long or a year-and-a-half-long training flow? How are we going to ensure that they're all going to be able to know how to do all the things they're going to do? We're not going to train them like we did in the shuttle, where we're going to do 1,000 ascents in the shuttle motion simulator because they have to do that many so they can figure out how this non-intuitive vehicle works. We're going to basically give them just a bunch of skills and assume they're going to sort it out and they're going to deal with the things. Or an EVA, a spacewalk, is going to crop up. They're going to have to go outside, and we're just going to give them enough standard skills that they're going to be able to sort it out. And so we discuss and debate all this, and we've had tremendous luck, even with the multicultural aspects of flying with cosmonauts, flying with European Space Agency astronauts and Canadians and Japanese, 15 nations all contributing to space station. And trying to make that work is a big challenge. And there's a huge amount of pressure for us to reduce the training flow so that we can make it more efficient. Okay, so this is the launch. I'll just let you listen to a shuttle launch real quick. So you get about 3 million pounds of thrust per solid rocket booster, 6 million there, 1.5 million for the three Space Shuttle main engines combined. The engines run for about 6 seconds so that the computers can check them out and make sure they're good before we light off the solid rocket boosters. And when they light, it's like somebody hit the back of your chair with a baseball bat. It's this tremendous amount of power. The vibration is shockingly great. Solid rocket boosters, the combustion is much more chaotic than it is in the Space Shuttle main engines or any liquid engines. So it's for the first 2 minutes predominantly under the power of the SRBs. It's a pretty violent affair. You go through the speed of sound at about 45 or 50 seconds. And if you put a microphone, you don't hear this, but if you put a microphone, a good condenser mic inside the orbiter, you'll hear this crazy sort of gradually building banshee howl that the orbiter makes as you go through the speed of sound and max Q. It's really, really impressive. At 2 minutes, the solid rocket boosters are expended. We have booster set motors, giant mortars that basically push the boosters away from their external tank. And it's 6 more minutes, a smooth ride, after which this happens, ET-SEP, external tank separation. And this is where we very quickly, in the post-Columbia days, flip the shuttle over on its back and start frantically taking pictures so that we can photo document that the external tank's in good condition. And then it's typically about 2 days to catch up to the orbiter after that. And the external tanks, of course, burn up. The SRBs, return to the surface of the water. They get towed ashore and get flown again. So our mission on this flight was to bring up 35,000-pound payload called the P3, P4 truss, and it's that module in the upper right here. It's about the size of a school bus. It's got 240 feet worth of solar arrays packaged in these 2 blanket boxes and 2 more on the other side. It's got a thermal radiator here, and it's functionally going to double the space station's electrical power output. So we're basically resuming construction post-Columbia. So we pull it out of the payload bay with the shuttle's robotic arm, hand it off to the space station's robotic arm, attach it, and then we do a series of spacewalks to get everything all activated. And then we deploy solar arrays, and then we release a bunch of launch restraints so that we can actually rotate that entire element to keep the solar rays pointed at the sun. Spacewalk's an amazing thing. So we only do those when we have to. It's a pretty hazardous affair, obviously, but it's glorious. I mean, the pictures you see from space, looking through 4 inches of glass, many panes of scratch pane, thermal pane, pressure pane, are still stunning. But the view that you see with your own eye when you're looking through just a couple millimeters of just crystal clear polycarbonate, where you can grab the space station, in a handhold here and push 1 million pounds of it behind your back so nothing human-made is in your field of view, and you're just flying like Superman over the Himalayas. It's just amazing. So the whole time you're on board space station, if you don't have a planned EVA or a planned spacewalk, every time an alarm goes off in the middle of the night, we get all excited. The crew's really psyched because you're hoping that something serious enough that you have to go outside, but not serious enough that you have to come home has just happened, And it's just one of those things, but anyways, it is great. So as the general mentioned, I went and taught for a couple of years at the academy. Loved that time. Just being around young folks excited about their careers, and it's a different experience. If anybody here, and many of you are, I'm sure, teachers and have had that experience, but it's different. I know I had a different deal because if you walk into the class and everybody jumps to attention and they're always there and they're always awake and alert, it's a little different than maybe the average experience in high schools or colleges. But it was really a great experience for me. But I wanted to come back. I wanted to do a long duration mission. So the 6-month missions that we do as standard on station, one mission we've done is 1 year. Scott Kelly and Mikhail Kornienko did. That's kind of our standard right now. It's tied to the on-orbit lifetime of a Soyuz spacecraft. It's an opportunity to do that. Now you're doing the things that you built the space station for. You're doing the science that the space station was made for. And to live there and truly become a creature of space, to go through the full adaptation, not to be a klutz banging off the walls, and to be there long enough that it's not like this was an imaginary thing that happened. You can finish a shuttle mission and come back and say, and you're so busy, you almost never spent the time to write those experiences to your permanent memory. You know what I mean? You come back and say, geez, did I really do a spacewalk? You know, what was that like? And if you live there for 6 months, you'll wake up often at night and you're transported immediately back to space station. You completely done that adaptation, and it's a pretty magical place. So I trained for 2.5 years with my two crewmates, Anton Shkaplerov, who's the Soyuz commander in the middle, and Anatoly Ivanishin, who is the Soyuz Flight Engineer 1 on the right side. Those two guys, first-time flyers. And great friends, like brothers. All our families, we all know each other and stay in close touch. A lot of the stuff we practice for all missions is to all the bad things that you don't want to have happen, like fires and depress or toxic atmosphere releases, things like that. Lots of science, lots of times in the simulator. A lot of times, a lot of the things are a little bit unpleasant, but it's good team building experience. It's the survival training for winter survival, water survival, things like that. And at the end of that 2.5 years, you are as closely knit as a crew as any set of American, crew members would ever be. So this was launch day, and actually the weather had cleared enough to get a shot of our rocket. You wouldn't even fly a Coast Guard helicopter in some of the conditions that you can launch a rocket in. We would never fly a shuttle like that. Shuttle, we need lots of weather. We're always planning for the cases where you lose a couple engines on, in first stage and have to potentially come back and fly that thing back to the Cape and land. But the weather here was just good enough for us. We had 2 meters of visibility inside the capsule. We could see all the way across, and everything was beautiful. Yeah. So we spend 2 days in the Soyuz, and it's tiny. It is so tiny. But frankly, it's a pretty good little sports car. Flies great, got lots of fuel, pretty zippy. And 2 days in that, though, after the 2 days, you really need to stretch your legs a little bit. So to fit in the descent module, so it's actually 3 parts there, and the part with the little green thing that's sticking up, that's a periscope. We use that for visual sighting of the space station when we get close. The Agregatny Otsek, this back part, is a propulsion module, power and computers, things like that. The heat shield is only on this middle portion. That's where you are for launch. That's where you are for landing. This ball part, the habitation, or Bitovoy Otsek, that part up there is where the docking mechanism is, and it's packed with cargo. There's not much room in there. But in the capsule, if you can imagine laying on your back right now with your heels against your rear end, your shoulder wedged against the bulkhead on one side, your shoulder wedged against your crewmate on the other side, and your toes jammed against the bulkhead. So even if you could get your feet, your knees stretched out, they couldn't go anywhere because there's not enough room, and there's a parachute kind of pushing, the parachute canister parts pushing your head back a little bit. It's pretty snug. So we catch up to space station and we do a fly-around maneuver. This is actually a shuttle one, but it kind of gives you a little bit of a sense of it. So space station expansive. You all know it's as big as a football field, 1 million pounds, well, 0 pounds, but 1 million pound mass. If you could put it on a big bathroom scale, it'd be that much. And it is huge. All the habitable volume is all down the vertical, the forward to aft stack. This is the Japanese module, really great module. European over here. We have an airlock over here. Our gym, bathroom, and cupola, where we have a window on the world, is over here. And there's a couple of modules that extend upwards and downwards. So the module that we brought up on that last shuttle mission of mine was this one right here. These are big radiators. So the problem in space is not to keep things warm, it's to keep them cool. So typically, you need to have big radiators to release, to reject all the heat that all the avionics tend to build up. You got an acre of solar arrays that'll generate 60 to 70 kilowatts of power. And we're about ready to upgrade all the batteries on board space station so you could even have more power generation and storage capability. This is the Soyuz in size. That's the size of the vehicle. Well, actually that looks like, yeah. So that's about the size of what it is, relative to the rest of the space station. So it is... It's pretty small. These are some of the facts and figures on the inside of space station. So if you don't do a spacewalk or you don't do a fly around, it's hard for you to get an impression of how intricate and complicated and large the space station is. Everything that you see, it's like you're inside of a giant rabbit warren, a very sophisticated one, lots of laboratories, and there's equipment and experiments covering every square inch. It looks like this. You only see typically one Greyhound bus, school bus size module at a time. You can see down the length of a few of them. We do a lot of operational activities like recovering or accepting spaceships that bring cargo to us. Some of them are automated like this one. This is a European ATV that comes up. Some spacecraft come up, we have to actually catch it with a robotic arm and attach it, using the space station's robot arm. And this is a view from the cupola with the robotic workstation all set up to do that. And if you look out the window on the left center, that's where the robotic arm manipulator is. So the end effector is huge. It's actually, if you just stood the end effector next to me, it's taller than I am, and it's probably about this big around. So it's well back in the distance. This is Don Pettit and Andre Kuipers getting ready to receive an HTV, a Hope Transfer Vehicle. It's a Japanese cargo vehicle, again, about the size of a school bus. So these vehicles will fly up alongside space station, then we'll power the motion control system down so they're free drift, tending to fall away at that point, and then we'll just reach in with the robotic arm and catch it. This one can bring up external cargo as well as internal. In your spare time, everybody becomes a shutterbug on space station. If you took and dropped a pixel on a map, every time somebody took a picture from the space station Expedition 1 to Expedition 28, right before I got there, this is what it would look like. And you can see those traces are basically, those little sinusoid traces are essentially the ground tracks. But you can almost, if you squint your eyes, see the a Mercator projection of the continents. After our expedition, this is what it looked like. So we took lots of pictures, and we didn't actually depress the shutter release a million times. What we did is we have really good cameras that can operate in an intervalometer mode automatically, and I would have, or Don Pettit would set up 4 to 6 cameras in the cupola, all firing away at half-second intervals for a couple of thousand shots. And then we make these aurora pictures or some of these, sequence shots that you'll see the movies out of. If you look out the cupola, just naked eye, this is the view that you would see out your living room window, so to speak, any given day. And so this is, of course, real unique. There's no big expanse of coral reefs like the Caribbean that we see from space. If the sun shines off the water, you sometimes can see great detail of tiny little rivers and maybe the Cape Cod Canal and little kettle ponds and all kinds of eddies and weird structure where the Labrador current's coming out of the north interacting with the Gulf Stream to the south. If you're really lucky, you might see something like this. So this is Comet Lovejoy, one of several Comet Lovejoys. Terry Lovejoy is an amateur astronomer in Australia and a very prolific one. And so this was our companion for about 2 weeks on station. It was a sun grazer that survived and shouldn't have, and had a spectacular tail that just extended millions of miles out into the void, glowing spectacularly. It takes a long time to get really good with the cameras, particularly the long lens cameras. Even though the shutter speeds are very, very fast, the space station is so fast that you have to have a very, very steady hand. And this is a composite, of course, of Manhattan. You orbit very fast. It takes you, an hour and a half to orbit the Earth, so you see 16 sunrises and sunsets every day. But they happen very, very fast. When the sun goes down, the planet comes alive in electricity. So that would be Manhattan, and with a night view, and easy to pick out Central Park and even Times Square area. London, just stunningly beautiful, and you never get tired of it. And it's amazing. You can shoot 500,000 pictures in 6 months and wish you could have got another 500,000 or could stay a little longer. It's sometimes hard to communicate that to people because it always changes. You'll never, any view of Namib, the Namib Desert, for example, like this, on any given day will never repeat, not in 6 months in my experience anyways. And it's stunning. You think of deserts as being monochromatic and boring, just expanses of boring, sand, but they're anything but. This is a dry riverbed in Australia. There's not very many human-made structures you can see from space, save these. So naked eye, you can see if you know where to look, and if the sun angle is low enough, you can see the Great Pyramids. This is the Namibia Desert, the skeleton coast back from the days of the tall ships on the right side of that image. And it's the most barren place probably on planet Earth. Life just cannot live there, hence the name Skeleton Coast. And it gets a millimeter or two of rain a year. But it's ironically, periodically, there'll be an upwelling of current from Antarctica that will suddenly create the most life-rich patch on planet Earth, like this algae bloom that you'll see. And it'll be, you know, an expanse that goes hundreds of miles. So this kind of gives you the scale of what thunderstorms look like. We think of them as really big. They're 10-mile high. They're, you know, towering above what our airliners fly at. From space, they still have three-dimensional character, even though you're at, you know, 250 miles above them. That 10-mile as it's coming by is, you know, it's amazing the structure you can see. And a single thunderhead, albeit a pretty big, impressive one, might look like that. Sometimes you'll see them building up over sandstorms. If you take those cameras, which are great, and you open the shutter for a good long period of time, you'll see things like this. So you see the sodium is the yellow of city lights, sodium vapor lights. Some of the greenish ones are mercury vapor, and these are lightning flashes. And this is the 100 kilometers of air glow in the upper atmosphere, and these are star trails. On planet Earth, if you want to see star trails that are circumferential or circular, then you would point your camera at the north or south celestial pole. On the space station, you just look arbitrarily out the left or the right, open the shutter, and you're looking about the pitch axis of the space station and what that axis happens to be pointing out on the celestial sphere. A fisheye lens looking out the cupola with all the 6 circumferential windows and the main window that looks straight nadir would give you a view like that. And there's up at the 10 o'clock position are some aurora, the green you can see. The red band that goes kind of to the 3 o'clock position on the right side of the view, that's part of the F region of the upper atmosphere where we bounce HF and amateur radio signals off of. And you can see that with those cameras quite nicely. This is kind of neat. This is you and me. This is what's called zodiacal light. And sometimes you'd be in space station and you'd be looking out the cupola and you would swear that the windows are fogging over, or you're going through, you know, a foggy patch coming up, and you know you're well above anything like weather, let alone fog. And what you're actually seeing, and if you look to the left or the right, and it would typically be in the direction of the sun. If you looked left or right, it would be absolutely inky black with tiny piercing, steady points of light that are the stars like they normally look, but they're all washed out in front of you, and they make this kind of pyramid shape. So what you're looking at is you're looking at the outline or the backlit Japanese exposed facility on the Kibo module, and that bright light there is the moon. It's overexposed. Directly below, you see the reflection of the moon in the Pacific, and then you can see the lights of Hawaii a little bit to the right. And then the center of that glow that's in the star field is offset to the right because the plane, what this is tiny nanoscale particles that lay in the plane of the solar system. They're just tiny bits of dust that have their date back to the predecessor of our sun. They were the remnants of a previous supernova explosion and probably one before that. And they're ones that were just a little bit too far apart to get close enough to coalesce into an asteroid or a comet or a planet or you and me. So it's actually the primordial material that made up everything in our solar system. And you can actually see it, pretty plainly. So we'll do a quick tour of the space station. I think I've probably gone a little bit long, and I'm thinking maybe we'll do a quick tour, maybe 1 or 2 other slides, and then we'll just open it up for a handful of questions. So you're basically flying from the Russian modules in the very back of space station, the service module. We're just going through the functional cargo block into the very first U.S. contribution, which is a Unity node module. That's one of the places we have dinners and meals together. The other place is at the very back of space station in the Zvezda service module. The lab, the U.S. lab, is the workhorse for the NASA-based science, and it is kind of a busy place. It's where all the work is done, and it's not the homiest kind of location, but it's the heart and soul of the science for the NASA program. Here we're going into the space shuttle. So the shuttle would dock in the front of the space station. We're going through a tunnel that takes you into the airlock. Again, this is where Bruce Melnick's crew had 3 EMUs in that tiny little airlock, and we couldn't even fit a cameraman and myself. So now we're going into the mid-deck of the shuttle. And you can see all the lockers on the forward wall. That's the kitchen, the galley. And then we're looking up into the flight deck access, and there's Chris Ferguson up on the aft flight deck of the shuttle. All told, from end to end, on the order of 280 feet. Okay, I'm just going to skip through a few things just real briefly and see if we can get a logical stopping point. This is kind of what our dinner table would look like. And if you didn't have everything taped or bungee corded down, this is what would happen. And there's Andre and Don. We do all the routine kind of mundane things that you do on planet Earth, but we do them very badly. We're pretty good pilots, we're pretty good engineers, some of us are good technicians and scientists, but we are lousy barbers, and so that whenever we do this, you'd be like, uh-oh, here we go, and it would be one slip, hey, sorry, Anton, hang on, and before you know it, everybody would be totally bald. And for the women in the crew, I don't even know how we would ever get by, but it was pretty brutal. So we'd either be doing that or wearing hats of some sort. So anyways, after 6 months on space station, the Soyuz, you climb back in and it's time to say goodbye. As if the Soyuz wasn't small enough before you left, now it's full of return cargo and you're 2 inches taller than when you left. So that kind of gives you a sense, and that's as roomy as it ever gets. And we're about to close a hatch, and it's going to get even smaller still. You get one glimpse of the station before you leave, that you're home for the last 6 months, and then pretty soon it's a wild and woolly ride home, and then a landing in the Kazakh steppe. And then the very first thing you do is you call home. And the beauty is now on space station, we can in truth call our families quite a bit. And thank goodness for that. So you actually feel probably more connected with your family, even over the long missions on station, than you might have been able to on a space shuttle, because you'd be lucky to talk to them even for a couple of minutes on a 2-week mission on a shuttle. So we're learning some real important lessons that way. So I think that's probably all I should do for prepared remarks and things. And maybe if there's a few questions, we can probably do that. I don't know if anybody has any questions for me, but thanks. In the back.
Did you speak to your crewmates in Russian and they speak back to you in English?
Yeah, so the question for the folks on the webcast, did I speak to my crewmates in Russian and did they speak back to me in English? So in general, we would speak, so the language of operations on space station is English. I would say on average, the proficiency of cosmonauts in the English language is better than the proficiency of the other crew members in the Russian language. So generally speaking, most do that. We probably, as a courtesy, so around the table, we kind of depend on the crewmates, but I was fairly comfortable speaking in Russian, and we would, depending on the topic, like if I talk with Anton, for example, or if I'm out with his family or his squadron mates or something, maybe doing something here on planet Earth and visiting with them in Moscow, it'll all be in Russian, and that's all good. And there'll be times where you're not even really thinking about what language you're speaking, which is kind of a beautiful thing. Taking me probably 20 years to get to that point, and it's fleeting. It comes and goes. And if I'm not there for 2 or 3 weeks, I find myself struggling to think of that word, and I definitely feel a little rusty again. But yes, sir.
Was your 2-inch increase in height an exaggeration?
Yeah.
And not, but whatever the increase was, how long did it take for you to get back to
Oh. Okay, great question. So the 2 inches, was that real or is that an exaggeration? That's an approximation. For taller crew members, 2 inches is how much you'll grow. 1.5 inches is probably pretty much standard. If you had a shorter, 5%, female astronaut or something, maybe it would be closer to the 1 inch. But 2 inches is pretty much spot on for us. It goes away in no time at all. So you go to space and there's a fluid shift that happens that makes all your wrinkles go away. So that happens. You get taller. What else? You lose weight. You actually lose all of it. But when you come back, all of that it gets undone very, very quickly. The height thing goes away within a couple of days. Probably goes away within a day, I would bet too. And if you do bed rest studies, if someone just lays recumbent on a bed for a period of time, and we do this to people, and to test out and model some of the things that we do on space station, and we find that people grow about that same amount too. It makes your lower back sore for a little while, and then it goes away. Yes, sir.
I noticed in the picture of the three of you together, the 2 Russian cosmonauts and yourself, you were all wearing the same spacesuit, the same type of spacesuit.
Yeah.
I thought they had different suits to the Americans.
Okay, so the question was about the spacesuit. In that picture with the three of us, Anton, Anatoly, and I, sitting there, we're all wearing the Russian Sokol, which is the word for falcon spacesuit. So the spacesuits typically are designed to interface with the spacecraft. So there's a lot of things that are done. In this case, so Russia, in this contract, so we flew cosmonauts on the shuttle, for example, and they wore our ACES, our Advanced Crew Escape System, those orange, pumpkin suits we'd call them, but they would wear those same suits and they would train in those, and those suits were optimized and designed to accept the flow rates for both the liquid cooling and the ventilation and the oxygen and all the rest. So there's a lot of the guts of the engineering of the spaceship is inextricably tied with the designs of the spacesuits. Same thing for the Sokol. It's got biomed, it's got comm, it's got oxygen, two oxygen, both emergency and regular ventilation. And so all those are designed and specifically made to work with that spacecraft. And in the emergency cases, like the survival cases, there's things about that suit that are optimized for the survival equipment that you might interact with as well. So it's a package. Yeah, but good question. I think you had your hand up before. Yes, sir.
How vulnerable is the space station to floating debris?
Yeah, how vulnerable is a space station of floating debris? This is a big, big deal. Yeah, I think orbital debris, micrometeoroid orbital debris, so it could be something that's man-made, it could be the remnants of satellites that have collided, or it could be things that have, slipped away during a spacewalk, or it could just be, it could be, there's a lot of stuff that we can see. That is a huge threat. We on planet Earth are swimming in molasses in a way. We don't think about it this way, but the Earth's atmosphere, the friction that it creates when you try to go fast against it, as airplane designers long ago had figured out, is a very real thing. It makes it very difficult to go anything else but the speed that fluid is going in. Absent that fluid in space, things go at the magic speed they have to be in a low Earth orbit. So if you have an 8,000-mile rock called planet Earth, the speed you got to be at is, the speed you have to be at is 17,500 miles an hour. And so things are quite happily closing each other at 17,500 miles for a combined velocity, upwards of almost 40,000 miles an hour. Kinetic energy is a major factor of this. So kinetic energy, 1/2 mass times velocity squared. Take a big V, square it. Kinetic energy, varies as the square, so it goes up tremendously. So rough order magnitude, if you took a grain of rice or a broken off chip, a tip of a pencil lead, for example, and accelerate it to that speed, it's got about the same kinetic energy as a bowling ball falling off the overhead, striking the front of a car going at highway speeds. The problem is, the diabolically difficult problem is, we can only see stuff that's about the size of your fist and bigger. So we can paint with radar, ground-based radars, things that are 10 centimeters, 4 inches, and bigger. We can see all that stuff, and there's 25,000 items right now that are all cataloged. Every time they come over the horizon, we refine the trajectory, and we move the space station to avoid the ones that come inside what we call the pizza box. It's a box that's kind of flat. It's fairly shallow in height, but it's got, I think, 15 kilometers by 15 kilometers in lateral distance. And if something is potentially going to impinge in that area, we will move the space station. Or if we don't have time, we'll do what we did for my crew. It was only the third time we'd done this, and that was, we found something that had enough uncertainty in its trajectory, and it was so late that with a space station that big, it would take way too much gas to move it. It was impractical. So we just started powering the space station down. We started up front, we powered things down, we closed hatches, moved back, closed another hatch. We basically created the watertight compartmentalization that we build into submarines and ships, so that if part of the space station got whacked, hopefully we'd be able to retain, habitability and the rest of it. So, and then we go all the way back to our Soyuz spacecraft, and we got our our little spacesuits nearby. We didn't put those on, and we close the hatch, and we sit here and we just wait for a loud noise. And that's happened a couple times. I think now maybe 5 times total. We've had to do a shelter in place. Okay, if you can, that's the stuff you can see. So if there's 25,000 things that are that size and bigger, there may be upwards of 500,000 things that are smaller than that, many of which could do a heck of a lot of damage to the space station. If you go outside and do a spacewalk, it looks like, and space station's been up there for a long time, you know, it's been pushing 20 years for those early modules, and you go outside and do a spacewalk, it's peppered with, looks like buckshot, you know, little holes and, you know, and handrails look like scuff paint. If you look up close though, there'll be a very sharp edge of aluminum that got, you know, almost smeared out like somebody took some Play-Doh and, you know, and made this hyper expanded crater. Very dangerous, easy to cut a glove with that. It's something we worry about. We stay up at night worrying about this. It's probably the biggest threat for humanity's access to space, not just the space station that we have. So the key is we need to get some really smart people to figure out how to find stuff that's a lot smaller and then to figure out how to get rid of it. Anything that's at 300 miles or thereabouts is probably in the course of months and maybe a year or two going to go away. There's enough drag there, it gradually reduces the orbit and it burns up. But there's stuff that's upwards of 500 miles, or it may have an apogee, a high point that's well above that, but it may come down and intersect the orbit of the station, and it might be there for 400 years, a threat that we can't even see because we don't know what it is because we can't paint it. So anybody that's a spacefaring country, it's incumbent upon all of us to be really responsible. If we launch something, you got to have a way to get rid of it. We can't. It's not enough just to leave something up there and just have it be defunct, occupying a piece of precious space. And the ones that are the most challenging of all are the polar orbiting satellites, the ones that go over the pole, because all those trajectories converge. And it was a couple of years ago that we had a defunct Russian satellite called the Cosmos, I think it was, that ran in and had a hypervelocity impact with an Iridium satellite and destroyed them both and created a cloud of debris that probably, I don't know what the percentage over the previous risk was, but it measuredly increased the risk to space station, and we're avoiding that stuff all the time. It's a big deal. Yes, sir, in the back.
The very first part of the presentation, you clearly have, you still have a real passion for the Coast Guard.
Yeah.
And the people. Is there any point during the NASA part of your career that you could say, I think this has been great, but I want to return to the Coast Guard?
Yeah.
Make flag, be the commandant?
Okay, so yeah, I don't know. There'd be others we have to ask that. So the question was, the first remarks I had, I talked a little bit about the Coast Guard, and I'll tell you, I feel, and so was there a point as my NASA career progressed that I thought about returning? I could have returned and potentially gone through a path that might have taken me up the flag ranks and done something like that. There could have been. I guess there could have been. I am really proud of the things I got to do, that I was fortunate enough to do in NASA. Do I feel like I really deserve to do all those things? I feel a lot luckier than I do feel good. You know, I really do. And it's a tremendous thing to be able to have the trust of my parents' service, the Coast Guard, to send me to be able to do that. It's a tremendous thing to be able to have the trust of the American people to put me on these spacecraft and go do the things I've been able to do. And I feel fortunate every day, and I'm very proud of that. But I'm as proud for all the other things that I did in the Coast Guard. You know, there's a couple hundred people, and this is not bragging. This is any coastie that's out there right now that's operational. A couple hundred people that are still walking, that came home to their families because my crew and me, you know, and I had a little part in it, were able to be there when there was nothing else, you know, no other option. It's just what the Coast Guard does all the time. So and that's always going to be something that's going to mean a whole lot to me. And it's a great service, and I think it's a wonderful proving ground, a wonderful training ground for doing these kinds of things as well, flying in space. For me to be able to go back to the academy and to reconnect with that organization and to maybe have a little bit of influence, you know, with some folks who are going to go out and do great things on their own too, and to try to, I'd always try to persuade them to do things like go to a ship first. I know you might want to fly, but by golly, go to a ship, because we need people who understand that, because you're going to be working with them out there, and soak it all up, enjoy it. There's so much stuff that we do. All the services are great. Aviation is a wonderful field, but the operational field in general is just tremendous. to be able to be in NASA, to be able to be an operator, this was kind of a unique thing. In the Coast Guard, in the Navy, in the Marine Corps, Air Force, Army, you don't get the opportunity to be gray-haired and still be climbing in cockpits or in spacecraft and doing things like that. Typically that stuff's long, go in your past. I know it is, and so there's always a part of us, I think, that deep down, are operators that are just passionate for getting out there. And for me, in the Coast Guard, it was kind of cool because the Coast Guard, there were more gray-haired, snowy-haired 05, 06 stick hogs in the Coast Guard helicopter community. I bet there still is now, than you could ever shake a stick at, and it's because it's so much fun. And so, anyways, so what's the point? I think I had a lot to offer, I think, with NASA. And once you learn all those things, they spend a lot of money, a lot of effort on you. And I thought when I get those 2 shuttle missions, I get it out of my system. But I was at the Coast Guard Academy and still thinking I really wanted to do the 6-month mission. That was great. Would I potentially be finding my way back to the Academy and potentially doing that? I think I'd be happier doing something like that than doing anything on the order of a flag office, kind of a flag officer kind of position, and just kind of influencing people, trying to get, it's incumbent upon us, and this is a great museum, a great institution to do this, to reach out to people and inspire them. These can be dark times if you look at the things that you have available to you that are being told to us every day about the world. But we have tremendous reason for hope. We have a great workforce. We have a great, brilliant youth right now that can have so much to contribute. There's no way that kids my age, I never thought I could be an astronaut, and there's thousands of kids right now that have no idea what they're going to be able to do when they get to be that age. We need, there's a lot of excitement going on in commercial crew. A lot of excitement going on in the NASA piece for exploration. And we need people to build these spaceships. We need people to go to Mars. We need people to go to the moon and put a permanent presence there. And I thought when I was a kid and Neil and Buzz were bouncing around on the moon, I thought that by this time we'd already have 100 bases on the moon and Mars would be old hat and we'd be everywhere else by now. Turns out space flight's pretty hard. It's like the hardest thing anybody's ever tried to do. And like Mike Griffin would say, we barely know how to do it at all. We really do. We're constantly surprised by how hard it is. But the things we learn, we can apply back here on planet Earth and do great things with them. But people that are thinking that right now, people that are growing up, that the 8-year-old, the 10, the 15-year-olds right now, they're going to be able to live on Mars and the moon. And we are going to become a spacefaring species. And when it comes right down to it, it's going to be a cooperative, multinational effort. We're going to be right at the front of the thing. We're going to be leading the way, and that's a great thing. I want to say one other thing. I know I'm going way long, but I think this is really important. There's a lot of stress and strife right now between countries all around the world, and it's really unfortunate. Everybody that flies in space, the thing that's really striking to you when you look at planet Earth, and many people have said this more eloquently than I ever could, is that there are no borders and no artificial boundaries at all. And its sense of permanence, its sense of invulnerability vanishes from space. Even though we're relatively close, you see what it looks like to see the curve of the Earth out that window, and you feel connected to it, and it's covering the bulk of your field of view. But dadgummit, that atmosphere is so small you can barely even think of it. It looks so fragile. And to fight over the things that we fight over when we're all the same, when we all have the same hopes and dreams for our parents, for our kids and so forth, to fight over the things we fight over makes no sense at all. So I think we really have to, whatever we can, to push the optimism, to push, to get our kids to believe in the things that they can do and create opportunities for them. And so maybe finding my way into a classroom again, be it at the Coast Guard or somewhere else, would be a good thing. I think it would be a good way for me to pay back this massive debt that I feel that I owe because of the things that I got a chance to do. Okay.
I'd like to, that was a perfect ending, by the way, but I want to extend it just because you've already, twice during your lecture, you talked about the fact you had failed to go to the Air Force, I did an Air Force thing today earlier, to the Coast Guard Academy, and then failed selection for astronaut.
Yeah.
And I think that's really important because that's almost the norm And the people that are doing these, making the application, have never failed in their life in terms of selection and the impact that it has on you in this first experience of, could you kind of expand on that just a little?
So that's a great point. So there's, if I look back at all the things I did, there's not a single thing that was worth doing that I ever succeeded at the first time. And I don't know that kids really think about it in those terms. So for me, whether it was getting into the Coast Guard Academy, whether it was getting selected for flight school, even getting selected for the astronaut program, doing anything that was worthwhile, I failed. I mean, I failed over and over again, and that was okay. And it sort of set the bit in my mind that I'm just going to keep plugging away. You know what? And it may not turn out even in the end, but the things that I learn in the process of plugging away will be for the better. I don't know that kids necessarily, young folks necessarily nowadays feel that, and it's really important. There's nothing, if it's worth doing, it's not going to be easy. It just flat out's not going to be easy. And if it's really worth doing, and lots of people are going to want to do it, the competition is going to be crazy. On the medical side, any number of things can crop up at any time. We wash out a lot of really great applicants for the astronaut program and for the academies as well, for things they never knew were an issue for them, and probably never would be an issue for them in their life if their life was going to follow a normal course or a more typical course. So I think it's just absolutely critical for kids, for young folks nowadays, to expect failure, to expect disappointment, and just decide that there's no way that that's going to dissuade you from trying again. Yeah.
Thanks very much, Dan. I don't think we could have had a better way to celebrate the 100th anniversary of the Coast Guard than in this presentation tonight. You covered all the things that we think are important when we talk about inspiration and how we try to hook people to want to know more and to strive for excellence, which is what we're really talking about here. And the thing that we keep running into is this first experience of failing, that that's the end of that one. And I believe persistence is one of the most important character traits that you can have. And we've talked to so many successful astronauts who said, I tried 4 or 5 times to get into this thing. And it's just coming back because they want to do it. And that's another issue or a point that NASA looks for is after you fail that first, what do? Do you come back or what? And so not giving up on your dreams is just an important ingredient, I think. You have presented that so perfectly tonight that I really thank you for being here. So I think we want to congratulate the Coast Guard for its 100th birthday. We want to thank all of you. This is the point where we normally thank the sponsors, and that's you, folks. So you're our home team, and thanks for everything that you've been doing for us and what you're going to do in the future. You know the routine, exit to the rear of the bus, and Captain Burbank will be available down in the lobby if you want to come out and say hello. So if you'll let us get out down this way, we'll meet you down there in the thing. Thank you very much.